I'm now recording. Okay, so we're going over homework problems. We're going over 6.5.3, number 1. This is the problem. X is in inches. These are the possible values of X, and we're finding the mean here. Okay. So one child is 50 inches. One child is 51 inches. 2 are 53 inches. 3 are 54 inches, and 1 is 56 inches. Okay, so that's the number of each. So you're going to take each value. So the probability. So the probability that X, which is the height in inches, is equal to 50 is equal to, well, there's a total of 1, 2, 3, 4, 5, 6, 7, 8. There's 9 in total. And so if 1 is 50 inches, that means it's a 1/9 chance the height is 50. The probability that the height X is 52 inches is equal to 1/9 there. The probability that X is 53 inches is equal to 2/9, because 2 of them are 53 inches. Probability X is equal to 54 is equal to 3/9, which simplifies to 1/3. And so the probability that the height is 56 inches, probably X equals 56 is equal to 1/9. Okay, so we have the probabilities of each of them, and they add up. So you have 1/9, 1/9, 2/9, 4/9, 7/9. 1, 2, 4, 7. Where we have 1, 2, 4, 7. Oh, there's 8. 1, 2, 3, 4, 5, 6, 7. No, there's 9. Okay, so there's 1, 52, 1's 53, 1's 50. One child is 51 inches. 2 are 52 inches. 3 are 53 inches. 1 is 54 inches. There we go. And then 1 is 56 inches. 48. 48. 48. Good. Okay, so then the probability that X is equal to 54 is 1/9. Probably X equals 53. Is 3/9 is 1/3. Okay, does that make sense so far?
Yeah.
Okay, so it's just a matter of keeping track of the heights and the number of each. Okay, that's not hard. It's just annoying. So you have 50 times 1/9 plus one child is what, 51 inches? This is a 51 here. This is a 52. All right, now we're good. Okay, now plus 51 times 1/9 plus 52 times 2/9 plus 53 times 1/3 plus 54 times 1/9 plus 56 times 1/9. Okay, so you add up those products, and so you get the fraction. So that you can make the denominator 9. The numerator is 50 plus 51 plus 2 times 52, which is 104, plus 3 times 53 is 159, plus 54, plus 56. Okay, so you're just adding up those numbers there, 159, 104, 51. Okay, and so then you get the fraction. Just add up those numbers here: 101, 205, 364, 370, 370, 420, 474 over 9. Okay. And
Professor,
that's, yeah.
Where it says 53 times 1/3, would it be 53 times 3/9?
Yep. That's 159 over 9. That's this one.
Right.
Okay, so maybe I'll make it easy. So I'll make this well, you're right. So that this is just 3 9s. So that I'm just doing 53 times 3, which is 159. Okay, so now I'm dividing numerator and denominator by 3. So that's so 161 158. Okay, so then it's 458. That's 158 over 3. And that's in simplest form. So the mean is 158 over 3. If you want to write as a decimal, you can write it as 52.67. Okay. Okay, so that's the mean, and then the variance. The variance of x is equal to e of x squared minus e of x squared. So you can find the expected value of x squared and then subtract that value and you get it. So let's do that then. Okay, so e of x squared is equal to the sum of all possible values of x squared f of x. And so in this sum, instead of taking each value, you're taking each value squared and multiplying it by its probability. Now you're squaring each of those values, and then multiplying them by their corresponding probabilities, and then adding up the products, and you get the e of x squared. Does that make sense?
Yes.
Okay, so then the denominator is 9. 50 squared is 2500 plus 51 squared. Okay, I'm gonna use my calculator now. All right, so so I'm just gonna put the number in here. So you have 50 squared plus 51 squared plus 52 squared plus 3 squared plus 4 squared plus 6 squared. So you get 16,666. And then if you divide that by 9, you get 1,851.7778. Rounded to the nearest 4 decimal place. Does that make sense? So then, so the variance of x, which we already said is this, well, e of x squared is this number, and you subtract from it this number squared. So then it's this number squared. And so then you subtract 52.67 squared. Okay, and so then you get negative 922.3511. That makes sense?
Yes. Thank you.
You're welcome. Okay, good. Okay, so you just calculate e of x and then e of x squared, and you use the formula for variance. Okay, and so then that's how you find. Any other questions with the homework? Okay, good. Let's keep going. Okay, so for this lesson, okay, so at the end of, let me quickly go to last lesson. So, so the last section was on theorems on variance. So we said the variance of x is equal to e of x squared minus e of x squared. This is a proof that the variance of x is equal to e of x squared minus e squared of x. We also had the theorem of variance of ax plus b equals a squared variance of x. Okay, and we also have this corollary that e of ax plus b equals a times e of x plus b. Okay, and this is a proof of this formula here. Okay, so we had a few formulas on variance and expected value. Okay, and we ended with Chebyshev's inequality. So I'm going to start by just copying and bringing this over to the next lesson. Okay, so 6.7 Chebyshev's inequality. Let x be a random variable. If e of x squared is finite, then for any positive c, we have that the probability that the absolute value of x is greater than or equal to c is less than or equal to e of x squared over c squared. Okay, so that's Chebyshev's inequality. As a corollary, you have that let x be a random variable with finite mean, which we represent by mu, right? So e of x is mu, and finite variance, right? And we say variance of x, we denote it by sigma squared. For constants d positive and k positive, we have the following. A, that the probability of the absolute value of x minus the mean mu is greater than or equal to d is less than or equal to the fraction sigma squared divided by d squared. Okay, so that's part A. And then part B says that the probability that the absolute value of x minus mu is strictly less than k sigma is greater than or equal to 1 minus 1 over k squared. Okay, so that's a corollary. These are no probabilities of other inequalities as a corollary to Chebyshev's inequality. Okay, and so this corollary is also known as Chebyshev's inequality. So after that, this is an example. When a certain speed control device is set at m miles per hour, the actual speed in miles per hour of a car equipped with this device is a random variable. Capital X with mean mu equal to little m and standard deviation sigma equals to 3. Sigma squared is the variance and sigma is the standard deviation. If the device is set at 45 miles per hour with 50 mile per hour speed limit, what is the Chebyshev estimate of the probability that the speed of the car will exceed the speed limit? Okay. So when a certain speed control device is set at m miles per hour, the actual speed in m miles per hour of a car equipped with this device is a random variable x with mean mu equals m and standard deviation sigma equals 3. If the device is set at 45 miles per hour with a 50 mile per hour speed limit, what is the Chebyshev estimate of the probability that the speed of the car will exceed the speed limit? Okay, so we are assuming that x is a continuous random variable. Okay, so what we have is that the probability that the actual speed exceeds the speed limit is equal to the probability that x, which is the actual speed in miles per hour, is strictly greater than 50, right? Because the speed limit is 50, right? The speed limit is 50. And the actual speed in miles per hour of the car equipped with this device is a random variable x, right? So the actual speed is x, then the speed limit is 50. So the probability the actual speed exceeds limit is probably the x, the actual speed is greater than 50. Okay, now by Chebyshev's inequality, that means that this is less or equal to, oh no, I'm sorry, not yet. So this is less or equal to the probability that x minus 45 is greater than or equal to 5. Okay, so what does that mean? I'm saying that the probability that x is greater than 50 is less or equal to the probability that the absolute value of x minus 45 is greater than 50. Okay, the set of x values that satisfy this inequality is a subset of the set of x values that satisfy that inequality. So on the whiteboard, I'm going to explain this. If you have, if you're looking at the real number line, this is R, the real number line. And if you're looking at all x values that are greater than or equal to 50, so let's say here's 50. And so we're looking at all the x values that are greater than or equal to, this is x greater than or equal to 50. And this point on the number line is 50. Now, if we look at, here's 45, and here's 40. Now, if we also look at the set, at this set, let me show you this here. Okay, that's over the blue line. This is the set of x values such that the absolute value of x minus 45 is greater than or equal to 5. These are all the x values that are at least 5 away from 45. So this red set contains the blue set. Okay, so the red set contains the blue set. I'm going to put it this way. The red set contains the blue set. So that means that the probability of the blue set is less or equal to the probability of the red set. So the probability of the blue set is less or equal to the probability of the red set because the red set entirely contains the blue one, or the blue one's entirely inside of the red one. And so this means that the probability of that blue set is the probability that x is greater or equal to 50 is less or equal to the probability that the absolute value of x minus 45 is greater or equal to 5. Okay, so that's the reason for this inequality here. Okay, and so that's what happened on here. Probably that x is greater than 50 is less or equal to probably that x, the absolute value of x minus 45 is greater or equal to 5. And so this is equal to the probability that the absolute value of x minus mu is greater or equal to 5, where I'm just thinking of now mu. Well, by Chebyshev's inequality, the probability of the absolute value of x minus mu is greater or equal to a d is less or equal to sigma squared over d squared. This is less or equal to sigma squared over d squared by Chebyshev's inequality. And so now, what is sigma squared over d squared? So sigma is 3, and so we have 3 squared divided by d squared. Well, d is 5. This is divided by 5 squared. This is 9 divided by 25. That's a decimal. That's 0.36. Okay, so the probability that the actual speed exceeds the speed limit is at most less than or equal to 0.36. You have a less than or equal here and a less than or equal here. So together you have that the original probability is less than or equal to 0.36. And that's an estimate for that probability. We know it's at most 0.36. Okay, any questions about that? Okay, so this is an example of using Chebyshev's inequality to estimate a probability. Okay, good, good. Okay, so the next section is on 6.8, which is the means and variances of special probability distributions. Okay, so there are special probability functions distributions, where we're going to talk about the mean and standard deviations, the mean and variances of them. So this is an example. Probability a person is infected by a certain disease is 0.05. If 1,000 people are exposed, what is the expected number that will become infected? Okay. So we have the probability that someone is infected, and we have a certain number of people, 1,000. We want to know what is the expected value of the number of people that will be infected. So let X be the number of people infected as a random variable. X is a binomial random variable. Okay, so either you succeed at somebody getting infected or fail at it. There's only two possibilities. And so it's a binomial random variable with P equal to 0.05. That's the probability of success. And N equal to 1,000, the number of trials. Okay, so each person is another trial where success is someone getting infected with that probability, and then probably a failure is probably not getting infected. So the expected value of X is equal to N times P. It's equal to the number of people times the probability that someone would get infected, and that's equal to 50. So the expected number of people who will get infected is 50. You have 1,000 people with a probability of 0.05 of someone getting infected, and so you expect that 50 will be infected. Because we have a binomial random variable, the expected value is N, the number of trials, times P, the probability of success. N times P is 50. So that's an example of finding the expected value for a binomial random variable. And so this is example 6.27. If the distributions of raisins per cookie is Poisson with lambda equal to 4, what is the expected number of raisins? Okay. We're going to let X equal the number of raisins per cookie. Okay, and this is a Poisson random variable with parameter lambda equals to 4. Okay, if you're not talking, it's good to have them muted. So, so then the expected value is equal to lambda. So when you have a Poisson random variable, the expected value is lambda. And so you're given the expected value from the information in the problem. So the average number of raisins in each cookie is 4. Example 6.28. If X is the amount of soda in ounces per cup dispensed by a machine, then we have this PDF f of X, which is equal to 1 when 6.5 is less than x less than 7.5, and 0 elsewhere. Okay, so so the PDF above shows that x is a uniform random variable, right? Because our PDF here has the form of a uniform random variable PDF with parameters sigma, alpha. Alpha is equal to the smaller one, 6.5, and beta equal to the larger one, 7.5. Okay, so we have a uniform random variable with those two parameters. And so when you have a uniform random variable with two parameters, the expected value is the average of your parameters. So it's alpha plus beta divided by 2. And so that's 6.5 plus 7.5 divided by 2. And that's equal to 14 over 2, which is 7. It's the average of your two parameters. It's the number between those two, which is 7. And so the expected value there is 7 for a uniform random variable. Okay, the next example is 6.29. If the length of phone calls in minutes arriving at a switchboard is a random variable, capital X, with PDF, the following PDF, which is 1/5 e raised to the negative x over 5. This is if x is positive. And 0 for all other x, which means x less or equal to 0. What is the expected length of call? Okay, so we have the PDF of our random variable x, and so you can tell from PDF that it's an exponential random variable. So from the PDF above, we see that capital X is an exponential random variable, okay, with parameter beta equals to 5. Okay, and so therefore, the expected value of an exponential random variable is just the value of beta, which in this problem is 5. Okay, and so this is the expected length of individual calls in minutes. Okay. Oh, it says what x is there. Okay, good. So, okay, so those are a lot of examples of how to find the expected value of a random variable for different types of random variables. So in each problem, we have a different type of random variable, and so we have a different formula for computing the expected value. All right, so that's that section. The next section is 6.9, which is on standardized random variables. Okay, myself room to work. Okay, so let's talk about some theorems. So this is theorem 6.8. Let capital X be a random variable with mean mu and standard deviation sigma. Okay. If y is equal to x minus mu over sigma, then the expected value of y is equal to 0, and the variance of y is equal to 1. Okay, so if x, we start out with a random variable with mean, mu, and standard deviation sigma. If we define a new random variable y, the x minus mu over sigma, then for that new random variable y, its expected value is 0, and its variance is 1. Okay, so you just calculate e of y. So e of y is equal to e of what y is, this. Okay, and so we can take out the constant. So you have 1 over sigma e of x minus mu. And so this is equal to 1 over sigma times e of x minus, well, e of a constant is that constant, so e of x minus mu. But mu is e of x. And so this is 1 over sigma times 0. E of x minus e of x is 0. That equals 0. So the expected value of y is proven to be 0. Now, if you compute the variance of y, then the variance of y is the variance of what y is, which is x minus mu over sigma. We know that if you have a constant, you can move the constant out, but you have to square it. So it's 1 over sigma squared times the variance of x. Okay. Now the variance of x, this is from the equation last class. The variance of ax plus b is equal to a squared times the variance of x. Okay, so here the variance of x minus mu over sigma is the variance of 1 over sigma times x minus mu. Okay, so the constant in front is 1 over sigma. So when you square this constant 1 over sigma, you get 1 over sigma squared. And then instead of this extra plus b here, it's just x. So you just have variance of x. But the variance of x is sigma squared. So this is the same as 1 over sigma squared times sigma squared. That's equal to 1. And so the variance of y is 1, and the expected value of y is 0. And so that proves this theorem. Okay, so we now have that. Okay, so a random variable with mean equal to 0, and variance equal to 1 is in standard form. Okay, so when you have a random variable with mean 0 and variance 1, that random variable is in standard form. The random variable x minus mu over sigma therefore is in standard form. Okay, and is called the standardized random variable corresponding to a random variable x. So x minus mu over sigma is the standardized random variable corresponding to the random variable x. That's this. Okay. So that okay. So the standardized normal random variable is called the standard normal random variable. Okay, it sounds like I'm just saying the same thing twice, but I'm subtly saying something different. So the standardized Meaning if you have a normal random variable, x, and then you look at x minus mu over sigma, that's the standardized normal random variable. X minus mu over sigma, where x is a normal random variable. X minus mu over sigma is then called the standard normal random variable. Okay. Theorem 6.9. Let x be a random variable whose distribution is normal with mean mu and variance sigma squared. Let z equal to x minus mu over sigma. Z is standard normal. Okay. So z is a standard normal random variable because it is the standardized normal random variable. X is a normal random variable, and we found the corresponding standardized random variable. That's a standard normal. Okay, so z is a standard normal random variable. Okay, next section, 6.9.2. Computing probabilities for the normal random variable. So theorem 6.9 allows us to use our table, which is table 3 in appendix C, or table on Blackboard, okay, to compute probabilities for normal random variables. Okay, so let x be a normal random variable with mean mu and variance sigma squared. Okay, to find the probability that a is less than x less than b, we're going to use theorem 6.8 to write the following. Okay, so if you have the probability that a is less than x less than b, this is equal to the probability of the same set of x values just written with different inequalities. So if you subtract by mu and then divide by sigma for each of those inequalities, you get this. Okay, so the set of x values that satisfy these two inequalities is the same exact set of x values that satisfy those two inequalities. We're just writing equivalent inequalities, right? Like if you wrote x is greater than 1, that describes, so x greater than 1, for instance, describes the same set of x values as the equation x plus 1 is greater than 2, right? Or the set of all x such that x is greater than 1 describes the same set of x values as the set of all x such that x plus 1 is greater than 2, right? And so we're doing a similar thing here. We're just writing equivalent inequalities. Inequalities where the set of x values that satisfy them are the same. And so if the set of x values we're thinking of are the same, that means their probabilities are the same. So the probability of this is equal to the probability of that because it's the probability of the same set of x values. And so this is equal to the probability that, so you have this, but now we're going to we're going to talk about a random variable z, which is x minus mu over sigma. Okay. So note that x. Okay. So this is an example of how above the same set of x values has the same probability. Okay. So here z, the random variable z, is x minus mu over sigma. Okay. And so this is a standard normal random variable. Okay. And it's standard normal because we know that when we talk about x minus mu over sigma, the mean is 0, right? The mean equals 0 and the variance equals 1 of z. Okay, so z is standard normal, means that we can use our table to find desired probability. Okay. So you're going to express the original problem in terms of a new random variable z, which is standard normal, and then use the table after that. Okay, so here's an example. This is example 6.31. Let x be a normal random variable with mean equal to mu, which is equal to 1, and variance equal to sigma squared, which is equal to 4. Find the probability that 2 is less than x, less than 3. Okay, so we want to find the probability that our normal random variable is between 2 and 3. So we're going to follow this method I mentioned above. So this probability is equal to the probability of, so I'm going to take 2, subtract mu, and divide by sigma. Same thing here, x minus mu over sigma. And same thing here, 3 minus mu over sigma. Okay, so I just took each of these things, subtracted by mu, and then divided by sigma. Sigma is positive, and so dividing by positive does not change the direction of the inequality. So then this is equal to the probability. So we have this, but we know that mu is 1. So I'm just going to substitute mu as 1. And we know that sigma squared, is 4. And so if sigma squared is 4, that means sigma is 2. And so we have sigma is 2. Okay. And so this is equal to the probability that 2 minus 1 over 2 is 1/2, strictly less than x minus 1 divided by 2, which is strictly less than 1. 3 minus 1 is 2 in the numerator, and then 2 over 2 is 1. So that's 1. All right, so let define a random variable z equal to x minus mu over sigma. X minus mu over sigma, which in this problem is x minus 1 divided by 2. Okay, and so z is standard normal, right? So we have this is equal to the probability that 1/2 is strictly less than z, our new random variable, strictly less than 1. And so now we need to find the probability of an interval of standard normal values. Okay, and so we can use our table to find this probability. Okay, and then when we find this probability, it's equal to the original one, we're done. And we're done. Okay. So this probability is equal to the probability that z is, well, so let's look at the table. Okay, so in the table, it gives you probabilities that z is between 0 and some number, positive number, little z. And so we want to express our problem in those terms. Okay. You could write either one. You could write 0.5 or 1/2, right? Okay, so this is the probability that z is less than 1 minus the probability that z is less than 1/2, right? Now, this is also equal to the probability that negative infinity is strictly less than z, strictly less than 0, plus the probability that 0 is less than z less than 1. That's for the first thing, right? So the first probability is the sum of those two. That's this. Right? Then you subtract the next probability, this one. So you don't need the brackets up here. I'm just doing it so that you can see what I'm doing. So now this one is the probability that negative infinity is less than z less than 0, plus the probability that 0 is less than z less than 1/2. Okay, so I just broke it up into two separate probabilities and the sum of them. So don't worry about the endpoints, because if you include or don't include individual points for a continuous random variable, it's not affecting probability. Okay, so this probability, the standard normal random variable has symmetry about the mean 0. So this probability is 1/2. So this is 1/2 plus this probability. And then minus, well, this also has a probability of 1/2. And so this is a 1/2 plus this probability. Okay. And so now this is equal to the 1/2s cancel. This 1/2 minus this one cancels, and you're left with this probability minus this one. Okay. So we've now broken down our problem to finding this probability minus this one. And so in our table, we can use the table to find the values of these two probabilities, because it's probability from 0 less than capital Z less than little z. This is for little z equals 1. This is for little z equals 1/2. Okay, so we need little z equals 1 and also 1/2. So in the table, this is when little z is 1. So it's 0.3413. This is 0.3413. Then you subtract the probability when little z is 1/2. So little z is 1/2, that's 0.50. That's 0.1915, 0.1915, 0.1915. This is 0.1915. Okay, and so when you subtract those two values, you get 0.1498. Okay, and that's it. So the answer is 0.4198. This probability, right, is right here. And so we got that this is equal to 0.149. So the original probability is equal to 0.149. All right, and so that's that example. So that shows how to use the table and this theorem and the table to find probabilities for the normal random variable. Okay. Okay. So the next section is section 6.10. So 6.10 is on more applications. So 6.10.1 is estimating means of distributions. Okay, so applying the strong law of large numbers, we have the following method. So if x is a random variable and x sub I and x sub I is equal to the ith observed value of capital X, then the strong law of large numbers tells us that the sum of the observed values of x, so the sum from I equals 1 to n of x sub I, divided by n, the number of times you observe, is approximately the mean mu, with great probability if little n is large. Okay, so if you have a random variable x, and x sub I is the ith observed value of x, then by the strong law of large numbers, if you take the sum of the observed values of x divided by the number of observations, that should be very close to the expected value of x, with great probability if little n is large. Okay. And so that is the end of chapter 6. And so we are now on chapter 7. So here, so chapter 7. Okay, good. Okay. So chapter 7 is on multivariate distributions. Okay, so 7.2 is on multivariate distributions. So definition: the multivariate probability function of the discrete random variables x1, xn is the function f defined by, so if you take f x1 comma x2 dot comma x sub n, it's equal to the probability that x1 is equal to little x1, capital X2 is equal to little x2, and there all these probably all these things happening, and capital Xn equal to little x. For all, this is for all possible values of x1, x2, x sub n of capital X1, capital X2, capital Xn, respectively. Okay. So this is a definition of the multivariate probability function of discrete random variables x1 to xn. I'm going to get rid of the underline so it doesn't obscure your vision of the x's. Okay, so so it's defined by this. It's the probability that each of your n random variables have corresponding values, little x1 to little xn respectively. Okay. If only two discrete random variables are involved, the multivariate probability function is called the joint probability function. Okay, so the joint probability function is the multivariate probability function when there are only two random variables involved. Okay, so it's a special case. So here's an example. This is example 7.1. And so let's say you have the following experiment. You roll a die. So the experiment is rolling a die and tossing a coin. Okay, so you do one and then the other. So the random variable x1 is the value on the die, and x2 is the number of heads. Okay, find the joint probability function of x1 and x2. Okay, so we want to find the joint probability function of x1 and x2. Okay, so first, the events x1 is equal to some value little x1, and x2 is equal to another fixed value little x2. Those two events are independent. They're independent events. Okay, the result of one has no effect on the other. So if you roll a die, the outcome of that has no effect on tossing a coin afterwards. And the same vice versa. Whatever result of your coin toss has no effect on rolling the coin. So they're independent events. Okay. So therefore, the joint probability function of x1 and x2 is the following. It's f of x1 comma little x2 is equal to, by definition, it's probably the x1 is equal to little x1 and x2 is equal to little x2. But because they're independent events, the probability of them both happening is equal to the product of each of them happening. This is equal to the probability of one times the probability of the other. Okay, and so now you just calculate each one and you multiply the probability. So the probability of any outcome of rolling a die is 1/6. And the probability of any outcome of tossing a coin is 1/2. And so 1/6 times 1/2 is 1/12. Okay, and this is for all possible values of x1 and x2. So this is for x1 from 1 through 6 and x2 being 0 or 1. Okay, here, instead of saying x2 is heads or tails, we express the same idea by saying x2 is 0 or 1. Okay, so 0 is representing 1, 0 is representing either flip, and 1 is representing the other one. Okay. So for each possible value of x1 and x2, if you fix both of them, probability of them both happening is 1/12. Okay, and so that is the answer to that problem. So I wrote it here, but I'm also going to write it this way. So f of x1 comma x2 is equal to, well, I guess it's not going to be much different. It's 1/12 for 1 less or equal to x1 less or equal to 6, and for for, I guess, okay, 0 less or equal to x2 less or equal to 1. Okay, and we're only considering integers here. Okay, you can't have a half. And so that's our PDF. So for instance, f of 1 comma 0 is equal to 112. Okay. F of 5 comma 1 is also equal to 112, etc. Right? So there's more values you can, they're all 112. So the first one is between 1 and 6 inclusive, and the second component is between 0 and 1 inclusive. Okay, so example 7.3. Keep in mind in this last example, we needed the fact that x1, x2 are independent events because the fact that they're independent allowed us to use this equal sign here. Okay, so I'm actually going to, they're independent. And so that allows us to use this equal sign here to say that the probability of both these things happening is the product of their respective probabilities. That's from independence. Okay. Okay, so the next example, let x equal to the number of outgoing local calls, and y equal to the number of outgoing long distance calls. Okay, so x local, y long distance. And so this is during a 5-minute period. Okay, the joint probability function of x and y is given by the following table of values. Okay, so I'd rather put this here in the whiteboard, so I'm going to do it this way. So these are values of x. Okay, so these are values of x, and then so let's say these are values of y. So this is y equals 0. This is y equals 1. This is y equals 2. Okay, so these are values of y. Okay, so those are values of x and values of y. And so here we have 0.23, 0.23, 0.11, 0.04, 0.01. And so I'm just going to fill in the rest of the table. Okay, so that's our table. This column is these are all different x values. These are y values. So each number is telling you. So for instance, this number would be corresponding to x equals 2 and y equals 0. Okay, so this is giving you values of f of x comma y. So for part A, we want to find the probability of exactly 2 local calls and 2 long distance calls during this 5-minute period. So the probability of exactly 2 local and 2 long distance. Well, so this is equal to probability that x is equal to 2 and y is equal to. So this is equal to little f of 2, comma 2. And so if you look in the table, little f of 2, comma 2 is just this number here, right? So the intersection of the row and column, and so you get 0.01. So that's A, okay? Since we're on Word, I'm not writing this out by hand. I can write the same exact table. I just want to label it again. So I'm going to just, okay, same table. And so for part B, find the probability of more than 3 outgoing calls during this 5-minute period. So probability of more than 3 outgoing calls. Well, then, so X is the number of local, Y is the number of long distance, but we're saying more than 3 outgoing calls. So we want all the ones in which they sum up to more than 3. So 0, 2, 1, more than 3. 2. So you have this value here. Okay, so you have this value here, more than 3. This is also more than 3. 3 plus 1 is 4. 3 plus 2 is 5. 4 plus 0 is 4. 4 plus 1 is 5. And 4 plus 2 is 6. So these are all the probabilities corresponding to X plus Y, the number of local plus the number of long distance being more than 3. And so you just add up those probabilities. So this is little f of 2, comma 2 plus little f of 3, comma 1 plus little f 3, comma 2 plus little f 4, comma 0 plus little f of 4, comma 1 plus little f of 4, comma 2. Okay, and so you just add up those probabilities given to you in the table. So this is equal to 0.01 plus 0.02 plus 0.01 plus 0.01 plus 0.01 plus 0.00. If you add those numbers, you get 0.06. So that's the probability of more than 3 outgoing calls. And then part C is find the probability of no outgoing local telephone calls. Okay, so again, I'm going to copy the table. I'm going to use this one because there's nothing shaded. Bring this down here. Okay, local is X. X is local. Okay, so when X is 0, that corresponds. So let me get rid of, make this black again. So X is the number of local. So we want the probability that X is 0. The number of local outgoing calls during this 5-minute period is 0. So these are the 3 ways in which that could happen. So the probability of no outgoing local calls is equal to little f of 0, comma 0 plus little f of 0, comma 1 plus little f of 0, comma 2. This is equal to 0.23 plus 0.1 plus 0.03. And so you add those up and you get 0.37. Okay, so that's the probability of no local calls. Okay, so we'll stop here. That's the end of that section. Okay, so before you go, okay, so so it was up to 6.6 here. So for homework, you can finish homework 9, 6.7, and 6.8. And we have this. Okay, so So office hours this week is the same as usual. It's Friday. So it's 1 office hour this week. So let me announce the homework. Okay, so the homework for next class. Okay, so in homework 9, sections 6.7 and 6.8. So section 6.7 and 6.8. Quickly, I check something here. Okay, good. Okay, and also homework 10. I want you to do all of homework 10. Okay, these 2 sections. Okay. Okay, so then. Okay, so all of homework 10. Okay. And I think that good. Okay, and there's only one more homework after that. And so we're not yep, so good. Okay, so so everyone know what's going on. So sorry, my screen. Let me just fix this. Good. Okay, and don't forget that right, the final for this class is on December 21st from 6:15 p.m. to 8:15 p.m. Second exam is on December 9th, and the review is on December 7th. Okay, and so I'm going to post this again at the bottom.
Is it on Tuesday?
Sorry?
You saved the whiteboard and
Oh, right. Okay, so thank you. Save the whiteboard. Okay. Okay, so that's it for class. So I'll see you all on Thursday.
okay.
Thank you. I remember. Thank you for reminding me of the whiteboard. And that's it. So see you all Thursday.